when we talked about intervals of convergence for power series, we showed that it had to be like less than the radius. So we always ended up with these open intervals. But in actuality, what we find is that sometimes at those endpoints, at the exact point where we have the center plus the radius or the center minus the radius, we might actually still have convergence. Sometimes that's even larger, but a lot of times what we'll see is that, well, we know that it goes from like -3 to 3, but it might actually converge at x equals 3 and diverge at x equals -3. So we have to be kind of careful about how we go about this, and the easiest way to do this is to use that theorem that we already used to find that interval and then manually test each endpoint, because it's only 2 more points. And we can use other series tests at that point, because we no longer will have an x. This will be replaced with some sort of number, so that we can use the standard test. Whether we want to use like an integral test or an alternating series test or whatever in the world we want to use, we can test the series at finite points. A lot of times you're going to end up using like an alternating series test here, to be honest, and you'll see the reason why. So let's do an example. Okay, I'm looking at this and I see, all right, what's my center? Well, it looks like my center is 4, because if I plug in 4 for x there, it's gonna eliminate all the terms. Actually, it's going to eliminate all the terms, period. So it's just going to completely be 0 at x equals 4, which, by the way, would be convergent, but it's not very useful. So we're going to say my center is 4, and I'm actually going to use a little bit of the board over here and say that my nth term is -1 to the n plus 1 x minus 4 to the n 7 to the n, and my n plus 1th term is -1 to the n plus 2 x minus 4 to the n plus 1 over n plus 1 7 to the n plus 1. Yuck, right? That's not super fun. So I'm also going to rewrite this in a way that probably would make the most amount of sense, which is I'm going to rewrite this as -1 to the n plus 1 times -1 times x minus 4 times x minus 4 to the n all over n plus 1 7 times 7 to the n. That's a lot of splitting out there, but this combines to that, this combines to that, this didn't change, and this combines to that. So I'm doing that conveniently because notice I'm matching this to that, I'm matching this to that, I'm matching this to that, and then this is going to match to n, but we got to be a little more careful. So when I take this limit using the ratio test, let's say I have that limit, so then I can plug this in. So I swapped that there. Just, I don't know, I think it's going to make it cleaner. So that's my n plus 1th term. This is my nth term. So I have -1 to the n plus 1, x minus 4 to the n n7 to the n. So immediately what I see is that these are going to cancel. Whoops, that's to the n. And that's going to cancel there. Alright, so everything cancels but the n here. So when I divide that n is actually going to come up top. So I have the -1 and the x minus 4, and then that n flipped because we're multiplying by the reciprocal, and I have a 7 and an n plus 1 on bottom. So now what I want to do is I actually want to split these two. I'm going to split this into the limit as n goes to infinity of -n for n plus 1. Now that's an absolute value, so we can actually get rid of that negative, times the limit as n goes to infinity, x minus 4 over 7. So this is just a constant relative to this right here, right? This is a limit in n, so this doesn't matter, or this is a constant relative to it. Now this limit is equal to 1. Hopefully you getting comfortable enough to see that. If not, apply L'Hopital's rule or do long division, whatever you need to do. So if that's 1 and this is a constant, we get x minus 4 over 7 is the limit. Now this limit is only going to show us convergence if it's less than 1. So what that tells me is x minus 4 is less than 7. Well, this is my radius of convergence. And my center is 4. So my interval should be 4 minus 7, 4 plus 7. So -3. -3 to positive 11 is my guaranteed interval of convergence right now from the theory. But what we want to do is we want to say, all right, well, does it actually converge at -3? Does it actually converge at 11? Well, let's find out. To do that, what we want to do is we want to actually plug in. So if we call this like a function here, we want to take f of -3. So if I plug in -3 and go there, now what I have to do is I have to be careful. How do I do this? I have a -1 to the n plus 1. I have this. So if I split this out, I can split this out instead as -1 times -1 to the n. The reason why I want to do that is because this becomes -10 to the n. But now I have -10 to the n and -1 to the n. I can actually multiply those together. And so I end up with this. Now if I take this particular series and I take the limit test, or actually in this particular case, if I do the nth term test for divergence, this thing's going to diverge. The nth term test for divergence on this is going to show that this thing just blows way out. It would be kind of annoying to do that with this much board space left, so just trust me that the nth term test here is going to show divergence. So what that tells me is that this piece stays the same because when I plugged in -3 it diverged, which means I cannot include it in my interval of convergence. However, if I take f of 11, and I take that piece, so I plug it in, now I get n equals 1 to infinity of -1 to the n plus 1, 7 to the n, for n times 7 to the n. Okay. And then I get that series, which that's an alternating series. That's like an alternating harmonic series. So if I take, by the alternating series test, since that term decreases down to 0 monotonically, and this term is alternating, then it's going to converge. So what that tells me is that this term is in fact actually included. So instead of being an open interval, I can include 11. So in this particular case, my radius of convergence is still 7, but my interval convergence is -3 all the way to +11.